We've been talking mainly about linear constant coefficient differential equations. Any general solution to this will have to have a component coming from the left-hand side for the homogeneous problem. And we know that for constant coefficients, this is just an exponential basis. And if we wanted to determine a particular solution to deal with the function on the right-hand side, we would use something like the undetermined coefficient method or the Green's functions method. All the techniques we've developed are great when the functions are nice and continuous, but they start to get a little bit problematic to solve and deal with when we have discontinuous forcing functions. And as an example of what I mean here, here's a definition, something called a piecewise continuous function. Things like sawtooth functions, so they kind of look like this, which isn't discontinuous, but it has a jump in the derivative. But you could also have what are called square waves. So you could have something that jumps discontinuously from one value to another. And all of them have practical importance. So we would like for our math to be able to deal with these things. The techniques we've got as they are going to have a hard time with forcing functions kind of like this. So we're going to have a new technique to solve linear constant coefficient problems. This new technique is going to be well suited for things with discontinuous forcing. Unlike what we were doing before, where we had to separate and find a homogeneous solution separately from a particular solution, this new method is really going to have no distinction between homogeneous and non-homogeneous problems. It won't care if there's something on the right-hand side or not. You're just going to be able to solve it the same way. A little bit further down the line, outside of the scope of this course, this method can be used to convert partial differential equations into ordinary differential equations. But for us, one of the big advantages is we are going to be able to convert our ODE into an algebra equation. What is it, right? What is this new technique? And so we are going to introduce what's called a transformation or a transform. And we're going to denote this transform with this scripty letter L. What operation gets rid of derivatives? Because we've got ODEs, right? We would like to get rid of them. And we know that integration will do the job for us. And so what we're going to do is define this transform. We're going to call it L, and we'll put a square bracket. And this operation, this transform, is going to act on that function in the following way. It's going to be an integral from 0 to infinity. We're going to define it to have e with a power of negative st, and then our function will be present. And so whatever function goes here is what ends up going in this spot. Now, the idea here is that we should think of our function as some point in this universe. And this transformation is going to take our function and convert it into something else. It's going to convert it into something else in some other universe. And let's start talking about what these are. Here, let's try to think of this as time. And the units of time are going to be seconds. This transform here has this contribution e to the minus st. And this we are going to define to be dimensionless. And if this has units of seconds, then this quantity s should have units of 1 over seconds. And from physics, anything that has units of 1 over seconds, we define this as a hertz. So this s is going to represent some sort of frequency. So if t is going to represent time for us, s is going to represent a frequency. Now the idea here is that when we take this operation L and we apply it to our function, we will be integrating it. And because we're integrating it with respect to t, there will be no more contribution t left. All that will be left will be some new function, but it will only be a function of s. And this is a function, little f is a function in what we call the time domain, whereas this result that we get is a function in what we'll call the frequency domain. So we are going to take a function that's a function of time and transform it into a new function. A new function that's a function of frequency. Now the little f has whatever formula, and capital F will be something totally different. But what's important here is that we are converting from the time universe, so the time domain, we're taking our function little f and converting it into a new function, capital big F of s, and this is now in frequency domain. This transform L is called a Laplace transform. What is the point of going ahead and trying to apply this strange integration? The idea now is we should consider our original motivation. I would somehow like to have this thing act on derivatives and kind of get rid of them. Okay, so if I take this and I plug it into our function, now remember I said that t is supposed to represent time. T we're going to take to be starting at 0. So that's why the lower limit of integration is 0, and obviously t could go up to whatever value we'd like, infinite. So that's why we're defining this to be 0 to infinity in our integration. So we're going to take that definition, e to the minus st f prime of t. Now, because this is an integral, one of the techniques you should have learned in your life is a technique called integration by parts. Integration by parts is essentially the product rule in reverse. So I'm going to take this thing, I'm going to say u is e to the minus st, and I'll say that dv is f prime of t dt. The point of integration by parts is to transfer derivatives off of the term v onto the term u. And this will ever so conveniently get me an f of t there. And when I take a derivative here with respect to t, I'll get negative s e to the minus s dt. Now, integration by parts says we're going to have a uv, so we'll have f of t e to the minus st evaluated from 0 to infinity minus this integral of v du. So it'll be f of t negative s e to the minus st dt. Now there's a little bit of work we can do here to manipulate things. 0 to infinity, we're going to take out this s, so we'll have positive s, 0 to infinity, f of t e to the minus st dt. Now, this thing right here, assuming that, again, all of these transforms exist, this thing right here is just by our definition the Laplace transform of the function f. So we'll call that capital F. Right. So in this particular case, we could think of this as, let's say, the limit t goes to infinity, f of t e to the minus st, subtract f of 0. And then this will be the following. We've got to make sure that there isn't some crazy amount of growth happening here. And what I need here is that I need f of t not to grow to infinity faster than e to the minus st goes to 0. Now here I'm making an assumption. Because I'm dealing with frequencies, I'm going to assume that this number s is a positive number, and that makes sense, right? Frequencies have to be greater than or equal to 0. So if this is true, then what we're going to find is that the Laplace transform of the derivative is just going to give me the following. It's going to give me s times the Laplace transform of the function minus the initial value here of the function. All the derivatives are gone. So there are no more derivatives. And that's one of the magical things about this Laplace transform. The precise definition of this is something called exponential order. Now, being of exponential order, another way to think of it is, okay, your function will always be trapped between some exponential. So m is some positive value and this alpha is some positive value. And it doesn't really matter what they are as long as they're always going to be entrapped like this. So another way to think of it is you could say, well, if I take the limit of my function divided by some exponential, this better exists. The limit better exists for some k. And we don't really care what the number is. It just needs to be trapped in there. Now, as a simple little example, the function e to the t squared is not of exponential order. And the reason it's not of exponential order is because if I take the limit of e to the t squared over some m e to the ct, I could evaluate this limit and think of it like this and say, okay, you know, e to the t squared, e to the minus ct over some m, and this will be a limit here. Now, if I write this, it'll be t into t minus c for any value of c, this limit's going to go to infinity. As t goes to infinity, this whole limit goes to infinity. No matter what the value of c is, eventually t will dominate. Eventually t will get bigger, and that whole thing will go to infinity. Now, the good news is that we don't really care about this. All of the solutions to constant coefficient linear problems, we already know they are all of exponential order. So we don't really have to worry about this. And so that really leads us to our definition of a Laplace transform. If the function f is piecewise continuous, so the kind of function I drew above on 0 to infinity and of exponential order, the Laplace transform of our function will be defined by this integral, and we're going to call it this thing capital F of s. This is what we call a sufficient condition. If you satisfy piecewise continuity in exponential order, it will be enough for your Laplace transform to exist, but there could be other functions that do other things as well. We are just looking at this particular set of conditions.